Good morning, everyone. Welcome to EasyPower's Arc Flash the Easy Way 2025. My name is Jim Chastain, and I appreciate everyone joining us today. As you might be able to tell by the title, this is on the Arc Flash study analysis phase. Those of you that weren't with us in the previous two sessions, you can find the linkage on the website, but they're 1-hour sessions as well. So last week we talked about data collection and system modeling. I've got a question I'd like to start with on a poll question, and that is, what type of devices are normally included, protective devices are normally included in the systems that you work on? Again, no obligation or liability, just trying to get some feedback from the audience on where your system's technology may lie. We'll be touching on the total. All right, looks like we have a quorum. Thank you. Here's how folks have weighed in on it. Looks like a large majority is both. So that was kind of a lame question. Sorry about that. And the second question is, which part of the system is the analysis is most problematic in terms of mitigation incident energy? So what type of equipment is most difficult for you to deal with mitigation? Again, no liability, or we will be doing primarily mitigation during the next part 4 session. So we will use the information gleaned from this particular poll question to make sure we address the areas that are most interesting to the audience. So let's give this another 10 seconds. And this opens up some other venues. You're welcome to ask questions through the question entry box on the GoToWebinar control page. You'll notice in the handout section I have a wide variety of information if you want to download it, including a copy of these slides. So let's see how folks have weighed in on this. So it looks like it's pretty heavy in the 480 volt switchgear and well spread across the other categories. So we'll be touching on all of those. It's for sure today, but more in depth next week. So appreciate that. Appreciate you joining us today. There were a couple questions that came up from the audience that I wasn't able to handle last week. And during the process of modeling, the question came in, show how to select a Mersen fuse with a specific part number. And I suspect part of the problem was one that we all share. Let me just show you what I'm talking about. And that is when companies have bought other companies and reissued the part number or reissued the data sheet, it may or may not cross over into the tool device library where we have the real old equipment and real old elements listed that may or may not be have the current brand on them. So what I do, first of all, is I Google the part number that I'm looking for and make sure I understand the description that they have in terms of series and the nomenclature that they use to describe the part. Then when I go back to EasyPower, I'm going to put a Mersen fuse here. in the utility feed. I'm not worried so much about its operation. I just want to use it to describe it. Open the dialog box. First thing we look at, so it's fuse only, so change the graphics. It doesn't change anything as far as the modeling. Manufacturer we know is Mersen. Now, the part type, the nomenclature talked about it being an amp trap, but when I look at the amp trap listings, I don't see that part number that we're looking for. So when I go back to the data sheet on the Google lookup, I notice it's also described as a current limiting fuse. So I'm going to go back and check that out. When I do, I see I have a closer description of what I'm looking for. So I'm looking for F62, so let's check that. Now the model, when we look at the models, I don't know which model it is, so I'm going to just use D because that seems to be part of the part number. But then when I look at the descriptions, I don't see maybe I do see it. I'm looking for a 50 amp fuse. So the point I'm trying to make is based upon what the choices you get can determine which part number you pick out. So it's just a single D that I see the 50 amps. So that's what I select. Now, this brings to mind how much time you should spend muddling around trying to look for this. If I had no other clues than what I'm going for, I might go in and use find style and say F62, 9F5062. And see what shows up there. That, interestingly enough, it gives me a couple of GE parts, but it also pushes me or lends me towards the current limiting description on Mersen. Sometimes this doesn't work. What I suggest is spend no more than 5 minutes trying to sort out the connection to the device library. If you can't find it, send a text or an email to tech support and say, hey, Jim said I should be able to find this part, where to go. Okay, so that's the Mersen. One of the other questions was 1584 covers 208 to 15,000 volts. Why not other voltages? And what's the purpose of the tool if it doesn't cover everything? Well, it turns out the focus by the IEEE test committee was this particular voltage range because it covered the most applications based upon the money that they had to invest in testing. But there are the potential for other arc flash calculations, and EasyPower has the ability to cover all voltages, and it's just a matter of knowing where to look in the tools. And part of it is understanding the type of fault you're going to see. So let me go back to EasyPower. To do that, I'm going to close this one. And open. All right, so other arc flash calculation methods. First of all, when it's outside the scope of 1584, which means 208 to 15K, you may run into the need to do a arc flash on a bus that's outside of that range. And what you have available to you from EasyPower, I'm going to go ahead and fault half cycle bolted fault and look at instant energy. If I've selected 1584, I don't get a result on this particular bus. But in this case, I'm getting a number, so what's generating that? I go to the short circuit options, arc flash hazard tab, advanced. The tool gives me the choice of applying Ralph Lee method to buses that exceed the voltage and exceed the current rating. So if I have that as my selection, I can see that now those calculations have disappeared. So they were the result of doing the Ralph Lee designation. So this is for three-phase bolted faults. So I'm going to go back to, and it's accessed through the advanced tab. Choose the alternative Ralph Lee method. By so doing, you'll get results of a three-phase application using Ralph Lee equations. And we can get results on open air for a three-phase result. But the problem is, or the suggestion is, an open air bus, very often we're more worried about a single line to ground fault. So how do you deal with that? Well, again, that's a different model than 1584 provides. And in EasyPower, when we have open air buses, it will use the single line to ground method that was first introduced in NFPA 70E Annex D8. By showing that, or selecting that, now we get a much more civil single line to ground fault incident energy. And then finally, DC. So if we go back to advanced, the DC equipment is analyzed with what's called the max power method. And the max power method has been described for systems up to 1,000 volts. If we have greater than 1,000, EasyPower will extend the method beyond that. And now if we look at the calculations on a DC bus, we'll be able to get arc flash incident energy there. And all this will give us the ability to do a label, and the designation on the label refers to the method that was used or not used based upon what method we're choosing. Okay, so that's outside the realm of 1584. Any questions? All right, let's jump into our subject for today. Okay, so for those of you that don't know, EasyPower makes software for electrical power systems that allows us to design the one-line diagram, do load calculations, automatically size the equipment, and then do short circuit analysis, arc flash, power flow, protective device coordination, reliability studies, harmonics, and stability. When you look at 1584, the release includes a .1 document that's referred to as an apps note, but basically it gives us some guidance on applying the 1584 model. And it suggests that we should compare results with and without motors, including virtually any motor or all motors above 50 horsepower. Then secondly, we should configure configurations that may support operation in any configuration that may be in place long enough that maintenance has to either inspect, adjust, or open up hot equipment while it's running. And so doing, they need to be aware of their incident energy exposure. And then these elements need to be labeled, and the labeling distance for the label, the working distance for the label, is going to be different than the working distance for hot work. And so that's, again, something else. Hot work will be done under a hot work permit, whereas a label will be on the equipment and available for anybody that's trying to take the cover off while it's hot. And then finally, there's a recommendation to make a judgment on whether to include or exclude the main breaker on a bus. And that's based upon whether or not there's an arc barrier between the incoming conductors to the breaker and somebody working on the bus that is protecting. So all that we're going to run into while we're doing the studies. I found the accident report in this particular event. That's a video that's on that's on the internet. It has to do with a meatpacking plant in Wisconsin, and it happened in 2003. The backstory is they had shut down the substation, switched over to standby generators on site to do preventive maintenance on the two substations. And once that was completed, they tried to switch back from the generator to utility power, and the 1 horsepower motor that's inside this cabinet wasn't switching over to the utility supply. So in this frame, we have two people standing, leaning on the doors, and one person kneeling that you can't quite see, presumably taking measurements. And the CC camera system picked up this particular image. So all three went to the hospital with body encompassing burns. At least one gentleman spent an extended time in the hospital. And you can see here 10 seconds after the event, someone is still pulling smoldering clothing off their person. This is indicative of, or an indication that the material that's used for this shirt is synthetic, and it melted and held the heat up to his body unnecessarily. I want to talk about three different things. First of all, the time, you can see the arc was extinguished well under a second. And so the 2-second rule doesn't really take any precedence here. But if we go back to one of these frames, let's see if I can find it. You can see this circular sphere, looks like it's about 6 to 8 feet in diameter. This is the fireball that caused the body encompassing burns that they all three experienced. At the center of this sphere is the plasma ball, which is where the heat was generated. And the rule of thumb, observers suggest that arc was probably 2 to 3 inches in length. And it's one of the restrictions as far as working distance. You don't want to be anywhere close to that arc because it'll vaporize anything that's within its range. Then if you notice here at the top, there's this vertical white issue. And this is reflected energy from the back and sides. And that means that these three were exposed to an amplified dose of radiated heat because they're looking through the only opening in a 6-sided cube. Now, according to the accident report, the company was fined $140,000, and the term willful disregard of employee safety was part of the report. People that have more experience at this than I suggest that it's probably a 12 to 15 calorie event at a working distance of 18 inches. So you can see how important PPE is, even in what's considered a relatively common energy level. Okay, let's move on. So we talked about it, prerequisite study being the short circuit and the protective device coordination. Short circuit gives us two things. It enables the ability to give us a 3-phase bolted fault value from which we will ultimately derive the arcing fault current. And secondly, it generates or gives us the compliance issues, if there are any, between the parts that are being subjected to the fault current and the data sheet that's listed in the model. And then protective device coordination is the ability to gradually increase the trip time of protective devices so that based upon a fault at some remote bus, the closest element to the fault will be tripping first. So let's go look at an example. And so I want to, excuse me. Okay, one of the things that I like to do when I first am sent a one-line diagram is see if there's any missing data. To do that, you use the database browser, which is this top icon in the center of the focus banner. And I like to look at the timing elements because time is everything in an arc flash. So I've organized or configured a view of this particular database that I call breakers. And what I'm looking for is a missing value in the short circuit interrupt. I don't see anything missing, but as I look for the manufacturer, excuse me, I see there's two missing elements here, BL2A and BL3A. If I go to the column and right click, go to the item on the one line, indeed, I see I have missing data on these two breakers. Well, according to my notes, they're exactly the same as BL1A. So I'm going to right click, excuse me, and copy, right click and paste in each of these other breakers. And then I look down here at my cables. The cables are supposed to be the same, and yet this one is out of whack. So I'm going to copy my cable and do the same thing. At that point, I know I have a complete one-line diagram. Guess I didn't get it correct. Okay. So the first thing we want to do is a short circuit analysis. Go to short circuit focus. I'm using these icons on the top left to characterize the fault that's going to be applied to each bus. It's going to be a half cycle. I'm on the top row. And on the second row, three-phase bolted fault, and then fault all the buses. Now, when we say fault all the buses, they're being faulted individually. So what we're seeing is the A phase for each fault. So if this bus faults, the A phase, all three phases are the same. That's why a bolted fault gives us a connection between three phases. So to keep it from cluttered, let's just look at the A phase. If this bus faults, we'll see 20,589 amps per phase coming from upstream, 138 amps coming from these loads, 426 from these loads. You might ask, where does this current come from? If I scroll down, I can see during that first half cycle with the fault on that main bus, this motor will contribute 321 amps into that fault. Likewise, all these other motors are part of that contribution. So the total available fault current is the number on the oblique. And so if this bus faults, it'll see a total in a worst case fault of 21,147 amps. Likewise, 15,849, 15,715. So that's my available short circuit current. I'm going to go up to my reports, and I'm going to create a high voltage and low voltage momentary report and click OK. Under the list of my windows, that report shows up. Now while I'm here, I want to calculate equipment duty. Equipment duty, while I'm looking at current, gives me this icon here on the second row called equipment duty. And what this does is it takes the rating that it got for each component in the system and compares it to that maximum current with certain constraints. And so if I invoke equipment duty, I see nothing out of the order on the lower buses, but I see a positive 6% and a negative 9% on these elements up here. Well, what the tool is doing is comparing what we call the threshold for equipment duty. Under my short circuit options, if I go to control, I've set up under the equipment duty catalog a number of negative 10% as the threshold based upon the number that I'm getting for the rating number we get from the data sheet. And so what this tool is telling me is if I have a positive 6%, I'm exceeding the rating that the current that we calculated is exceeding the rating on the bus at some point. Whereas here, if it's negative 9%, it's saying it's within that 10% threshold, but it's still compliant. So again, I want to report. So if I go to short circuit reports, equipment duty report, let's just include only the violations. Now that I click OK, I can go up to my list of windows. Let's look at equipment duty first. So the fuse is rated for 55,000 amps. In a worst case fault, it'll say 50,270. Well, again, it's within the 10% threshold, but it's still compliant. Whereas the main, turns out it's the main bus that's rated for 20,000 amps. And in a worst case fault, it's going to see 21,147. I want to go back and check my notes to see where this number is coming from. It could be a mistake in data entry. It could be that the system's actually been over dutied and it just hasn't experienced the massive fault, the worst case fault. But in any case, we need to investigate the situation. Once we're through with that, we can go back, save these reports, and export them to Excel. While we're at it, all our reports show up under the list of windows. Let's look at the low voltage momentary report. Now, during the modeling discussion, we talked about how important the X over R calculation was for a particular testing environment for a protective device. The manufacturer and the standard used will give us what that X over R factor is. EasyPower calculates the X over R at every bus, and based upon what the difference is, it will apply a correction factor so that in looking for the three-phase momentary current, we're always comparing apples and apples in terms of the environment that the voltage is being rated for. So I'd save a copy of this. Every report I can export to Excel or to Word. I can copy and put it in a report as it is or print it out. So I'm going to probably save this. I go and look at my other report, which is the high voltage. There's only one high voltage bus, same kind of information, and I'm good to go for short circuit analysis. Now what you'll find as we get more into the discussion, we can simulate a three-phase bolted fault, single line to ground fault, a line to ground fault, and a line to line fault. And these will give us different values for current, and they will come into play based upon what type of protection we're needing in our system. So that's short circuit analysis. Let's see what's next. Okay, coordination is not required for an arc flash study, but it's a convenient time to do it. It's usually something that's required, well, it's required by the design team, but it's not required by the NEC except on emergency systems and critical loads. So it's a good idea in terms of doing an arc flash study to at least check the coordination, whether the customer's asking for it or not. So we're going to look at Smart PDC. So these are files, by the way, that are available in a tools installation under the tutorial list. So here we have a typical radial system. We have a couple different voltage levels. The utility comes in at 13.8 and the loads are at 480. We have a couple large motor control centers and protective devices. The module that we use for coordination we call power protector, but we label it coord on the focus banner. Once I go into coordination, I get a new set of icons on the left-hand side. First thing I want to do is to look at current. So I'm going to look on the top row at a half cycle, three-phase bolted fault, and I'm going to fault a single bus. So let's pick out this motor control center 2B, and I'm going to fault it just that single bus. And what the tool shows me is if this bus faults, the fault current will include 21,070 amps coming from upstream, and the total available fault currents on the oblique. So the difference between the two is about 2,200 amps, and that's motor control, the motor contribution from the motors inside the motor control center itself. Now, as we're looking at this, I see illuminated, I'm looking at current with a single bus fault and coordination focus. The tool makes available to me this icon on the second row called sequence of events. And once I invoke that, now the tool shows me what the chronological tripping order is for every device between the fault and the energy source. So if this bus faults, this breaker trips in 190 milliseconds, this breaker trips in 35 seconds, this fuse would trip in 33 seconds, and the relay would have tripped in 290 milliseconds, and they're flagged red because they're out of order. You might say, well, that's interesting stuff, Jim. Can you show me a report? If I go to PDC options, bottom right-hand column, create a sequence of events report, under my list of windows, I will see a sequence of events report that shows me that same information in tabular form. So this is a way to check to see if you have coordination issues for the largest load, or at least a remote downstream load. So I'm going to close this report. So that was for a single bus. If I click in an open area, open white space, so that no bus is selected, and I fault all the buses with the lightning bolt, there's too much data to show me the results on the one line, but what do you think is going to be shown under this sequence of events report? That's right, all the buses, and the upstream tripping order of any bus, of any device, if that bus were to fault. And what I see is in most cases, it's the relay that's out of whack. So this is not the tool to do the coordination, but this sequence of events report gives me an idea of how much time I need to allocate to the test for doing coordination. If I've only got one or two devices out of whack, it could probably take me an hour or so to knock it out. If I've got 15 to 20 devices that are miscoordinated, it may take a couple of weeks. Now again, on an advisory note, if the customer's not asking for it, it may be worthwhile to say, hey, you got coordination issues, and it may be something we want to deal with before we complete arc flash studies. So coordination goes something like this. I'm going to scroll out until I can see the largest load on the bus. We're going to coordinate for the loads on switchgear 2A. The largest load is this 250 horsepower motor. The motor control centers have larger total loads, but no individual motor that large. So I'm going to left click and drag, and select that largest load, and the next 2 or 3 levels of upstream protective devices, and then plot the TCC curves. Now I'm going to reorder some labels and take off the one line. Now these plots are color coded from my little one-line diagram. And so the violet motor, you can see it corresponds to this violet chair. Here the relay is green, which I can see on my one line. The turquoise breaker is BL2C. The magenta breaker is BL2A. The fuse is this red ribbon. So the motor starting curve is based upon the locked rotor current, which describes this lower portion, and then the full load current, which will be at the longer time line. Now we want it to be able to run the motor at full speed without affecting our protective devices. As I hover over, so before I go there, any time current plot, so we have time on the vertical axis and current on the horizontal axis, and it's log. And right now we're plotting in the 480 volt domain or reference point. Any time current plot to the left of the chair would be considered a normal start. Any time current plot to the right of the chair would be considered an abnormal start, and we need to have some protection for the motor if the current would get that high. And then for sure, this little stubby line is a thermal damage, mechanical damage point for the motor. We in no time want the current time plot to be up and to the right of that stubby line. As I hover over the breaker trip plot, the tool shows me what the dial settings are that gives me this performance. I can left click and drag, and it tells me what dial I'm adjusting to change the performance to match the curve. So I'm going to snug it up to my motor starting curve, and I'm going to pull a long time pickup down inside of the thermal damage curve. So now my motor looks like it's in pretty good shape. Now, in the old days, well, first of all, time is everything when it comes to arc flash. So if we have a fault on this bus, we look at the instant energy before we get started here, we can see right now I'm sitting at a 16 calorie exposure for anybody that has to work on this bus while it's hot. But I can see that that's probably because of the tick marks that the tool put in when I fault that bus. It's probably due to the fact that the relay is the next device tripping. Evidence of the fact that my current is intersecting the green line before it gets to the next breaker up. Well, now in the old days, when you bought a breaker from a manufacturer, folded up inside the box with the breaker would be a piece of onion skin paper, and this plot would be printed on it. And so to coordinate, it mounted to stacking up all the onion skin paper for the motor, the breakers, the relay, the transformer damage curve, the fuse, and then the cable damage curves, which are these two parallel lines over here. There we go. So coordination amounted to stacking up all the onion skin paper on a light table and scrunching them around until you could see light between each of the curves, stick a pin in it, and call it coordinated. Well, in this day and age, when we can plot all these devices on any voltage reference we want, right now we're at 480, we could just as easily plot it on a 13/8 scale by setting this bus to the reference point. It doesn't change the relative performance, but it gives us the reference in the 13.8 volt domain. It kind of begs the question, Jim, if this computer is so smart, why can't it do the coordination thing itself? because it's just a rule-based situation, and their recommendations are not even legal standards. Well, the answer to that question is this icon here at the top called Smart PDC. This is a rule-based module that applies the rules to the devices I've selected. It goes through all the loads that are listed, and then all the dial settings and combinations of set points for any adjustable device, and then comes back with a list of recommendations for settings for optimum selective coordination. So when I click on this bus, you'll see for about a second and a half, a rectangle where it's running through all the calculations. It's going to replot the curves based upon the rules we've given it, and then give me an updated instant energy report. Okay, watch, because it happens fast. Here goes. So just that fast, it went through the dial settings. It didn't like me having this breaker snugged up to the motor starting curve because of its overlapping this asymmetric tail. And if the way it was set, I would get tripping unnecessarily on every motor start that had this current subjected through the breaker. So it pushed the breaker out, but it kept a long-term pickup inside the damage curve. If you look at my instant energy, it increased. In fact, it almost doubled the instant energy. It went from 16 to 38 calories. Well, that's testimony to the fact that coordination is very often contradicts mitigation. So this is strictly reliability improvement of the system to apply selective coordination. You can see it pushed the green relay up. It pulled the magenta breaker down. It can't do anything with the fuse, but every time I click this button, the tool generates a report that tells me what it did. And that report shows up under my list of windows. So I'm going to look at my auto coordination phase report. Here's the first breaker. There's what it's coordinating with. Here are the original settings. Here's the new recommended settings. Here's the second breaker, what it's coordinating with, motor protection, what the original settings were, what the recommended settings are. Now again, it can't adjust the fuse, but it verifies the fuse is following the rules we gave it. And one of those rules is transformer protection, and the tool is saying, hey, this fuse is not cutting it as far as recommended values from the National Electrical Code. Well, it turns out the backstory on this device, on this system, is that it was originally built with a 125 amp fuse, but on some graveyard shift, the electrician replaced the fuses with what he had in the truck, which turned out to be 175 amps to keep the plant up and running. Turns out he didn't realize that he was decreasing the reliability of the transformer, so we need to do something with that before we go any further. And then the results on the relay coordination. So I'd save a copy of this report. I'd save a copy of this plot. As I close it, it's going to ask me if I want to save it. I'm going to give it some kind of clever name like switchgear 2A. Let's do it motor 2A. And it'll be there under my open TCCs next time I want to look at it, or saved with the project. Any questions about selective coordination? Okay, so if I'm done with that, we've completed data collections, constructed the one line, done our short circuit analysis, protected device coordination. The next step is calculating instant energy. And we're not going to do mitigation today because we're running out of time, but we'll be jumping on it big time next week, or next part 4. So now we're going to calculate the arc flash results. So let's close this. I mentioned that these are available in your tutorials, down below on the start page, here's Smart PDC that will connect you to that same like a one line that I was working with. There's short circuit analysis, and both of those are available in the tutorials. So now I'm going to open the last one. And we're going to walk through the arc flash calculations, and we'll be doing labels next week. So I right protect mine, and okay, so everything's been coordinated, short circuit calculated. I'm ready to march forward. So short circuit focus, again, the icons on the top left and when we're in short circuit describe the profile of the fault that we're inspecting. When we're in arc flash though, what characterizes the short circuit are under short circuit options, arc flash hazard tab. And this allows us to pick out the standard that we're using. This original example was built back before 2018. So we want to use the updated 2018 standard. Again, it recommends excluding the main, so we're going to exclude the main on all the buses. We're not going to worry about the 2-second rule the first time through. I'll talk about it. We're going to use an integrated method. The standard recommends using a dynamic assessment of arcing current. EasyPower calls this the integrated method. And what it does, when we're calculating instant energy during the first cycle of the fault, it's going to integrate using half-cycle current. During the next 8 cycles of the fault, it's going to integrate energy accrual using 5-cycle current. And then if the fault lasts longer than those 9 cycles, it will integrate further incident energy accrual with 30-cycle base. And so we're going to click OK to accept these setups. We're in short circuit focus. We're going to fault all the buses. And then we're going to use the arc flash guy to do the instant energy calculation. Now, like I started out saying, the next step, the very first thing you want to do is make sure these calculations are being done correctly. And to do that, you utilize the icon here at the top called Arrange for Arc Flash, because that gives me simultaneous view of the arc flash hazard report spreadsheet down there on the bottom and my one-line diagram. It also lets me isolate on each bus if I want to. It's by double-clicking on the bus. So looking at the calculations for bus 2, it's a 480-volt bus. BL5 is an upstream device, and that's because we've excluded the main on the bus, so that's making sense. We've classified it as switchgear. The electrode configuration by typical values is vertical in a closed box. These dimensions and electrode gap come from the standard because we use the default values. The arcing fault current, the bolted fault current is 15.5. According to the model, the maximum arcing fault current is 10,204 amps. The time to clear the arc based on BL5's TCC curve is 3/10 of a second, 30 milliseconds rather. And so that gives us an instant energy of 0.8 calories and a working distance of 18 inches. So that sounds good, except this isn't a piece of switchgear. You say, well, Jim, this isn't a switchgear. In fact, I know there's a barrier. This is a motor control center, and I know there's a barrier between the incoming conductors to the breaker and the bus that we're trying to protect. So how do I deal with that? Well, again, the setup on short circuit options that we used, these are global settings. So I don't want to change those. What I want to do is go back to the database edit and change the settings for this particular bus. So first of all, it's not a switchgear, it's a motor control center. So we select motor control center. Second, under Arc Flash Hazard tab, instead of using the global options, we're going to include the main. And that's local setting for just this bus. Now I mentioned that these were values for working distance, electrode gap, configuration, and enclosure size were standards, and these numbers, when we use default from the library, these numbers came from the 1584 standard itself. But you might say, well, no, my data collection team said the electrode gap wasn't 25 millimeters, it's actually 45 millimeters. So I can user specified for this bus only. And my electrode configuration is vertical in a closed box, but the enclosure size is different than the 20 by 20 by 15. So let's make it match what the data collection team got. All right, so again, this is data that came in for that particular bus when they were doing data collection. So now I'm ready to click OK. Let's go back into short circuit. Let's fault this bus. Let's look at a range for arc flash. Now it's still a 480 volt bus. BL4 now is the upstream tripping device because we include the main. Equipment type is a motor control center. The dimensions on our enclosure now are different, and our electrode gap is different. And you'll notice even the color of the type is different, and that's because previously the reduced arcing current was more conservative. Now our 100% arcing current is more conservative as far as the results for that breaker. And so the tripping time is 17 milliseconds, which gives us a slightly higher incident energy, but it more accurately reflects the condition of this of our system. Any questions? So if I'm happy with this setup, I'd click in an open area, fault all the buses. And so doing, my arc flash hazard report now shows me all of the bus detail. And so it looks like I'm in pretty good shape. Now, you'll notice we don't have any calculations made on this bus. If I go back to the database edit, this bus is a utility bus. And so none of our people will be working on this. So in fact, if I look at the details on it, under arc flash hazard, I've excluded it from calculations because there's no protective device above it. And if I included it, it would end up being a very large number that would scare people. And since we're going to have nobody in the area working on it, we'll leave it up to utility to deal with that arc flash calculation. Sometimes people ask, okay, what if I want well, we'll talk about this next session, but my label for the transformer could be based upon voltage on the primary side and available fault current on the secondary side. That requires custom labeling. So the answer is yes, we need to probably pay attention to that. Okay, so that makes our arc flash situation relatively complete. Any questions on arc flash, short circuit analysis, coordination, or setting up 1584? All right, that's all I have for today. Next week we'll be doing mitigation and labeling, and I do want to emphasize, well, I'll talk about this more next week. The label the label that's going to be generated is one that we're going to be going on the equipment itself. But if I'm going to do work on this bus, that working distance may be different than what we put on the label. And so EasyPower allows me to do a work permit identified with the work conditions that needed on this particular bus. And based upon what that work is, I can predict that I'm going to have a 6-inch working distance because the person's hand's going to be in the area. And so if I select that and generate the hot work permit, the tool will show me the working distance for that particular task. So it includes the working distance, the voltage, the incident energy, which is considerably higher than the label because of our shorter proximity. And then it requires sign off for preparations and management, including upper management, to show that they're aware they're putting employees in elevated hazard conditions. So we'll get more into label and permitting next week, our next session. Okay, thank you all for attending today, and I look forward to engaging you with this part 4, when we will get way into labeling and to mitigation specifically. We'll talk about hot work and the integrated method. Thank you for joining us. You will all be receiving an attendance certificate via email, and look forward to engaging with you next week or next session. Have a good day.